Excuse me. Okay, today we're going to learn some techniques for solving limits. We're going to fill in that gap. What did you do with my icosahedron? Oh, okay. No problem. I can't see it from here, so I thought you did something sick and twisted to it. But it didn't. Oh, it's fine. All right, you watch it, man. Make sure it doesn't do anything weird with it. Yeah, good job. We're going to learn some techniques for filling in that step 2 of the solution process. Step 1, plug and chug. If that doesn't work, then the algebraically manipulate or simplify part of it is what we're going to cover today. So we did that already, and you should be able to understand the limits, properties of limits. We'll get to that. That's pretty easy. Come up with some strategies. I'll show you a couple other techniques that'll help you simplify the functions a little bit more to make it easier to take a limit. We're going to talk about the dividing out and or the rationalizing technique. That's not so fun, but it's not that difficult also. If we have time, which we did not have time 4th hour, but we might in this class, we'll talk about the Squeeze Theorem, also known as the pinching theorem, also known as the sandwich theorem. One theorem has 3 different names. It's very confusing. And you should also be able to get at least 20 grapes in your mouth without trouble. Okay?
And they be dehydrated grapes.
Maybe raisins. Those would be raisins.
Can they be raisins?
Well, they can be whatever you like. It's, as long as you can get at least 20 grapes in your mouth, I'm okay with it. Can anybody not do 20 grapes? Really? Have you ever tried?
No, I'm guessing.
Which one's that?
I don't want to kill myself, so like choke.
The odds of choking is pretty slim.
It's like playing Chubby Bunny. When you look up
Chubby bunny.
Chubby Bunny.
I'll ask again. Chubby bunny?
You just
It's
stick
when you stick
marshmallows.
marshmallows in your mouth.
And you
Mouth.
just say chubby
It can
bunny.
melt down to your mouth.
So you find a poor mouse and you shove it full of marshmallows. As it's squeaking, you just keep shoving marshmallows into it until what happens? So you shove marshmallows in your mouth? What
So
does
you can't
chubby
shove
bunny
it
have to do with
You
it?
until you're like chubby bunny
Yeah,
Chubby Bunny after every single time.
So you end up like chop off on
Until you choke.
Yeah. And that's what you crazy kids these days do for fun?
I say we go for a treat Tuesday.
I hate marshmallows.
where's
It's one of the few foods I won't eat.
Why do we not have a treat? Why are
I
there
think that's a us problem.
I mean,
I don't need, no, I'm gonna take the hit on this one. Let's move on. Properties of limits. Ooh, that sounds so impressive. Okay, first things first. 3 theorems you should know. 3 theorems that are really simple if we break it down. Okay, so notice first of all in the theorems, B and C are numbers. Okay. We're using B to represent any possible number, C to represent any possible number. What does the graph of y equals some number look like? Let's say, Gesundheit. Let's say, Gesundheit. Let's say 2. What does the graph of y equals 2 look like? What kind? Horizontal line. So if I have this horizontal line that goes on forever, does it matter what x value I have? Because if I go up to the function, what will I always get as the y value, aka the limit? 2. Okay, that's what that's saying. Second part, what's the graph of y equals x look like? Good. That'll be very helpful in the slideshow. It's a 45-degree line. Let's suppose I choose x being 4. What's the y value? 4. Let's suppose x is -10. What's y? Let's suppose x is a gabillion. What's the y value? A gabillion. So what happens if I pick any x and plug it into the function? What will I get out of it? I will get that same value. Okay. These two, well, this one, number 2, is easy because it's just a plug and chug. As x approaches 2 of the function x, we'll plug in 2. Look what I got. Oh, 2, done. Here, this one people freak out in number 1 because they don't see an x. So if this is as x approaches 2, well, where do I plug into 2? I have nowhere to plug into 2. Oh my God, I can't do it. It does not exist. And you freak out. If you think about it as being a horizontal line, then the value becomes fairly simple. Part 3. Okay, so we got 1, we got 2, Part 3 is the same as part 2. It's just a plug and chug. Plug 2 in for x, and you get 2 to the nth power. We good? All right, now the fun stuff. Don't write this down. Now, the reason you shouldn't write this down is because I want to explain it first. Copying things down and not understanding them is not helpful. So don't write anything down that you don't get. Let me paraphrase this first. If you want to write down the paraphrase, that's fine. You want to copy this down, that's fine too. But we're starting with two functions, f of x and g of x, and we have values for the limit. Like we've talked about already, the value here is going to be L. Since we can't use L again, we call that one K. So the first one says scalar multiple means if you take a function and multiply it by some number, then the limit is just going to be the limit times that same number. So in other words, if I want to find the limit of 3x squared, I can just find the limit of x squared and then multiply my answer by 3. Does that make sense? Good. 2, 3, 4, and 5 all follow the same format. I'll say it first and then you can process it and understand. The limit of a sum is the sum of the limits. Shall I say that again? The limit of a sum is the sum of the limits. Number 3 is product. The limit of a product is the product of the limits. So in other words, find the limit of both of them, multiply the answer by each other, and you're done. Quotient's the same thing. The limit of a quotient is the quotient of the limits. Barring, of course, that k is not equal to 0, because if the denominator is 0, all bets are off. It's the end of the world as we know it. And I feel fine.
That was clever.
Did you get the reference?
Yep.
Name the pen. REM.
Yeah. I was gonna say that.
You got it?
Yeah.
Good. Bonus points. And then number 5, the power. The limit of a power is the power of the limit. It sounds like I'm talking gobbledygook there, but it's actually, it sounds like a motivational speaker.
Can you repeat the first one?
The scalar multiple one?
Yeah.
Yeah, the limit of a number times a function is the limit of the function times the number. Now, why are we doing this? We really don't use this that much. Actually, let me scratch that, start over. You use this a lot. You've been using this a lot, you just don't know it. Okay, so for instance, this problem. Before I even go through the rest of the little clicky things, what's the answer to the problem? What's the limit as x approaches 2 of 4x squared plus 3? Huh? I'm sorry?
No check.
What'd you call me?
No check.
19.
The night?
19.
Oh, 19. Is it noche night? No, what's night in Spanish, anybody?
That's no check.
Noche, see? No.
That's no check.
Buenas noches. See? Buenas tardes. See? See, noche is night. It's also 19. That can get pretty confusing. When do you want to meet? Let's meet at 19.
7.
19 o'clock.
7 we're meeting?
1907 p.m.
See, if you're on 24-hour time. Right. I'm very confused. 19 is the correct answer. How do you know it's a plug and chug? 2 squared is 4 times 4 is 16 plus 3. Now, what allows us to just plug and chug is all this fun stuff. So I took the limit of a sum and wrote it as the sum of the limits. I took a scalar multiple and wrote it as the scalar times the limit. This is one of the theorems we had early on. If you got nowhere to plug in an x, it's just the value of the function. And then lo and behold, you get the answer. Now, are we going to be doing all these steps? No, it's ridiculous. It's just what allows us to plug and chug. Okay. Bueno. We answered that question already. All right, this one gets a little weird and requires a little bit of an explanation. So we want to take the limit of the nth root of some function, some variable. What's important is that we look at whether or not that n value is even or odd. And why is that relevant? Well, can you take an odd root of a negative number? Can you take an odd root of a positive number? Yes? Yeah. The cubic root of 8 is 3. The cubic root of negative 8 is? Negative 2. Did I say 3? Sorry, I confused myself. Let's back up. What's the cubic root of 8? 2, right, because 2 times 2 times 2 is 8. What's the cubic root of negative 8? Negative 2. So we're good to go there. What's the fourth root of 16? 2. What's the fourth root of negative 16? No solution, undefined, imaginary number, icky, bad, stay away, no, we don't like it. And that's what this is saying. You have to check to make sure if your nth term is positive or, sorry, even or odd, will affect whether or not you can accept certain values for x or certain values for c. In other words, you can't take the fourth root of a negative number because it will give you an imaginary number, which we avoid like the plague. Am I going too fast? We're good? Okay, so strategies for finding limits. We talked already about plug and chug. We did something similar to this over here, so I don't know if we need to review it because it's the same type of problem, but what's the first thing you do? Plug and chug. Doesn't work. 1 minus 1 is 0 over 1 minus 1, which is 0. 0 over 0 is bad. Second step, algebraically manipulate. So factor it. It factors down to this, x squared plus 1, sorry, x squared plus x plus 1. Then what do? Cricket. Plug and chug again. Ba-bum, ba-bum, ba-bum. Plug and chug. And we get our answer of tree. Okay? Pretty straightforward. That's easy. Factoring cubics, which we have up here. Sometimes you'll be factoring the difference of squares. Remember, difference of squares factors, sum of squares does not factor. Okay, we ready for the fun to begin? Yes, sir. Oh, you're ready. You were, okay. Thank you. I appreciate that. Okay, how about that guy? It seems fairly nasty. It's actually not too bad. What do we do first? Plug and chug. Does plug and chug work? No. Nope, get 0 over 0. So therefore, we need to come up with a different strategy. I'm going to give you a word. You tell me what it means. What is a conjugate? Ellie, you first.
It's like the opposite.
Like the opposite? What'd you say, Melissa?
So it's something you multiply it by?
It is, but we have to know what it is before we multiply by it. Okay, so let's say I have x minus 1. What's the conjugate of x minus 1? Nope.
1.
X plus 1. Now, why do we care about the conjugate? Well, what happens when I multiply this out? What do I get? Good start. Okay, the middle term goes bye-bye. That's why we're going to use the conjugate a lot, because it will allow us to get rid of the middle terms. And in this case, simplify things a little bit so that we can solve the problem. So what's the conjugate of that numerator? Squeaky shoes.
Is it the square root of x plus 1 plus 1?
Beautiful. So I'm going to multiply the top by the square root of x plus 1 plus 1. Can I just randomly multiply a numerator by a value? What must I do? Yeah, so we're going to multiply. Well, first of all, I plugged and chugged. It didn't work bad. So then I multiply by the conjugate. Conjugate over the conjugate. Why is this allowed?
It's equal to 1.
It's equal to 1. Okay, so multiply that bad boy out, see what you get. If you're doing it correctly, it might seem a little confusing because the bottom will get simpler, but the top doesn't seem to get much simpler. That might be bad English, but just go with it. That's why we're in math class. After you multiply it out, we're done with the algebraic manipulation, so therefore the next step is to?
Nothing, just.
I'm sorry, what? Nothing, just cry? Is that what you said?
Yeah.
Okay. Plug and chug, thank you. Are we okay with that top? Square root of x plus 1 times the square root of x plus 1 is x plus 1. The middle term disappears, and therefore negative 1 times 1 is just negative 1. And again, look at the bottom. It didn't get any nicer, but hopefully, if we did our math correctly, things will clean up a little bit. So the obviously 1 minus 1 is 0. Then the x's cancel, and lo and behold, we're taking that as our simplified version. Then you plug and chug, and oh, it works so nice. And we get
Wait, can you go back? Like this slide?
oh, sorry. Yep. There?
Yeah.
That awkward silence. Where you don't really know if you should say anything, you just let it go. It's true. Usually silence is the best approach there. You let it become more organic and you just let it go. Don't have to talk about it. Exactly. If it's gonna happen, it's gonna happen. It's like, right. Like free flow. Instead of forcing. You don't have to. Yeah. Gesundheit.
Thanks.
You're welcome. Let's try that again. Abby, you good?
Yeah.
Are you following what I did?
Yeah. Why? How come you can't just take out? Like I understand, like it works this way, but how come you wouldn't take out x like out of the whole fraction?
From the original part?
Well, like where you cross out the x, I did like x and then parentheses 1 over square root x plus 1 plus 1, and then it turned out differently because.
Wait, I lost you there. You did what? This step, you mean?
Yeah.
Okay.
because I kept the x like outside of it, so like why do you just can you just like for the whole.
Well,
I don't know.
you have to cancel it because if I plug and chug again for 0, these will cause everything to screw up.
Yeah.
So our goal here is to get rid of things that are going to prevent us from, or we want to get rid of things that are causing it to be 0 over 0.
Okay.
That x is the main instigator. So by getting rid of that x, it allows us to go back to plugging and chugging. Plugging and chugging or plug and chugging? Plugging and chugging, right? Because we're doing it. Both are. Okay, let's move on. Three theorems in one. It's all the same theorem, it's just called different things. I personally like the sandwich theorem, but you can call it whatever you want. We're going to stop soon because I don't want to go too far. But I will kind of introduce the sandwich theorem, and then we'll start tomorrow by finishing up the slideshow with the sandwich theorem. So there's two parts of this theorem. The first part of the theorem, which is called the hypothesis, and then there's the conclusion. We're going to talk about the hypothesis first. Okay, so it goes like this. We've got three functions, and this is our hypothesis. We're requiring that f of x is always between g and h. So here's g up on top in purple. Here's h down on the bottom in blue. And then you see f squiggling in between there, but never leaves being between h and g. You got?
Should we draw it?
It's entirely up to you. I would probably draw it. You can see then why it's called the sandwich theorem. You got two pieces of bread and a piece of bologna, or ham, or turkey, or cheese, salami, just cheese.
Grilled cheese.
Grilled cheese. Okay. But sometimes in a grilled cheese sandwich, the cheese comes out from between the bread.
Same with any kind of sandwich.
I'm sorry?
Any kind of sandwich.
How would your bologna just randomly get to the other side of the bread?
Well, no, if you can hang out. The bread's smaller than the meat.
Like out of the sides of it.
Yeah.
Like not through the bread.
Oh, I see what you're saying. I guess I just always have bread big enough. You could trim up the bologna. I never understood why bologna is round, but bread is square or
Why does
rectangular.
pizza come in square box? Why does pizza come in square box?
Great question. 8 hot dogs, 10 buns. You know what I'm saying? You got to do a math problem if you're having a barbecue. Find least common denominator or whatever that whatever that thing is called. Greatest common multiple. Right. You're in the middle of Mariano's with a calculator trying to figure out how many packs of each. Obviously not designed by a mathematician.
Are all hot dogs like that?
Why would you get
Most of them are, yeah. Is it, wait, I think I have it backwards. I think it's 10 hot dogs, 8 buns, right?
Yeah, that's
Oh,
right.
yeah.
Yeah, it's 4 and 4.
Makes you buy more buns, you spend more money.
So you're suggesting it's an evil, sinister plot by those that design
And
groceries?
then I noticed I thought, why is the meat less expensive than the buns?
I'm sorry, what?
Why is the meat less expensive than the buns?
Right.
Yeah, that's true.
So that meat is nasty.
That's why I don't eat hot dogs. That's why.
My goal in life is to die and never know exactly what's in a hot dog.
I don't think.
I just stopped eating them.
Therein lies the rub. The guys that are making it don't even know what kind of stuff they throw in there. Let's try this, Bill. All right, throw it in
But then
there.
they like advertise it with like kosher, and I was like, okay, how kosher are they really? Like, do you actually know what you're putting in there, or are you just like doing the same thing as any other hot dog? You know, they just like
Yeah, like when they say 100% beef, that they don't tell you what part of the cow.
exactly. You're getting something nice.
Mr. Reeves, I had to watch the video like for notes the other day, and it's like really funny to hear like all this stuff. Like when I watched the video for notes, and we just
Always. What were we talking about in that video?
I don't remember, but I don't know, it's funny. Something
it?
yeah.
Awesome. So anyways, ignoring something like a peanut butter and jelly sandwich, the idea there is we keep the lunch meat in between the sandwiches. Okay? So the first part of the hypothesis is that F has to always be between H and G. The other thing that has to happen is G and H have to approach the same limit. So notice that G is getting closer and closer to this dot at C, and H is getting closer and closer to this dot at C. So you all are fairly bright. What do you think would happen to F?
It passes through the limit.
Yeah.
Same way.
If you take your bologna sandwich and you eat all the crust off, and then you smash down the sandwich, the bologna's not going to magically come flying out of the sandwich. It's going to stay between the bread. Does anybody ever eat their bologna sandwich that way? Nobody eats a bologna sandwich that. No one's.
No one eats
Bologna is such a gauche lunch meat. We don't eat it anymore. We eat only 100% ham. Turkey made from free-range turkey. Mommy only buys the best lunch meat. When I was growing up, there was only one lunch meat, bologna. That was it. Sometimes, if your parents are feeling kind of crazy, they make fried bologna. You ever have fried bologna? Yeah. Oh, so gross. You put a piece of bologna in a hot pan and just go, and then you try to press it down and it does. So then you get a dome of bologna that's burned around the edge and grease stuck in it, and then you slap that onto a piece of bread, and that's supposed to be good. I'm having flashbacks right now. I'm getting a little sick to myself. What's that? Yeah, no kidding. Yeah. We're bringing in fried bologna for Treat Tuesday next week. All right, we're going to stop there. We pretty much have the idea of where this is going to go. We're going to come up with the idea that if we can keep F between G and H, then the limit of F is going to approach the limit of the same thing as G and H. But we'll talk about that tomorrow. We'll finish up with this. There's an example. We want to use the Squeeze Theorem to solve this kind of problem. We're going to eventually look at, come on, one more. There we go. Here, come on. There. We're going to solve that guy. By the way, that function is that. Ooh. Yeah. That's saucy. Okay? So we'll do that tomorrow. Again, oscillating function.
Yeah. Can we get our test back?
No, not everybody's taking it. Good question, though.